My name is Todd Girardin, an assistant professor at Cornell University, and I'm excited to share research in which we use a policy learning algorithm to optimize the design of an energy conservation intervention. In this project, we use utility data on home energy reports, which is a behavioral energy conservation program in which utilities mail letters to households in order to encourage energy conservation. We take advantage of randomization in those programs in order to provide evidence of heterogeneous treatment effects. That is, that the effect of these letters on household energy consumption is different across households and different in a way that's correlated with household characteristics. And we use this variation as motivation to use a policy learning algorithm to optimize the targeted assignment of these letters. The idea of this approach is to use data to select a rule based on household characteristics that will maximize a measure of welfare in the target population. So you can think of social welfare that we want to maximize here as the average of outcomes Y1 for individuals who are assigned to treatment and outcomes without treatment Y0 for individuals who are not assigned to treatment. But these are potential outcomes Y1 and Y0, and we can't observe both for every household in the data. Instead, we can rewrite this welfare model as the expected outcome with no treatment and the gain in treatment relative to that baseline from treating a subset of households. The optimal policy here from a utilitarian perspective will be to decide on the treatment rule pi that will maximize that welfare gain. It's isomorphic to maximizing welfare. And the key insight of empirical welfare maximization is to solve the sample analog of this population problem. So we want to search over potential candidate policies, pi, in order to choose the one that will maximize this measure of welfare in the data. The advantages of this approach for policy learning are that it directly integrates economic decision-making and inference. It has desirable convergence properties, and the rules are very simple and transparent and easy to implement. In order to apply this method to home energy reports, we have to first recognize that the goal of home energy reports is to minimize energy consumption. And so we recast this welfare maximization problem as an energy consumption minimization problem. So we look at two outcomes. First, electricity consumption, and also separately measures of cost that account for both the value of, or the cost of electricity consumption, and also the cost of program administration. And then we'll search over two separate policy classes to find the optimal rule. The first set of policies is quadrant rules. This is easiest to see in a graph. Here I'm graphing pre-treatment electricity consumption on the y-axis and income on the x-axis. And within this characteristic space, we will search over all the possible quadrants and choose the one that maximizes the measure of welfare in the data. And as you can see here, the optimal rule would be to treat households with baseline electricity consumption above 500 kilowatt hours per month, and all households except those with very low income. The second set of rules we use are called cubic rules, which are very similar but a bit more flexible in their boundaries. And here I've overlaid that cubic rule on top of the quadrant rule, again with baseline electricity consumption on the y-axis and household income on the x-axis. And you can see a very similar pattern. The optimal rule will treat households with high pre-treatment electricity consumption, although the cutoff for that treatment based on pre-treatment electricity consumption will vary with income. We find similar results when we use a range of alternative characteristics. So here I'm plotting analogous figures with pre-treatment electricity consumption on the y-axis and house size on the x-axis, and then house age or construction year on the x-axis. And we find similarly here that the rules tend to treat households with relatively high baseline electricity consumption. It's nice to know the shape of the rules, but we also care about the savings that are associated with them. And so what we find is that targeting achieves significant cost savings. Here I'm plotting the results from the actual randomized control trial relative to a baseline of no treatment. So this trial generated cost savings on the order of $1.50 per household per month. But if we treat based purely on baseline electricity consumption, we find that we can increase that to about $3 per household per month. And if we use additional characteristics and both sets of rules, quadrant and cubic rules, we find similar and somewhat larger electricity cost savings on the order of $3 to $3.25 per month. In conclusion, we apply a policy learning method here, a novel approach that hasn't been used in the literature before, in order to optimize the assignment of home energy reports. And we find that targeting using these transparent and easily implemented rules that aren't really black box in nature can still yield significant gains relative to a randomized controlled trial.